lot of time last couple of months trying to make Python work together with native extensions like C, C++, Rust, and similar things. And this talk is going to cover this for the most part in the context of Sentry and how you can do similar things yourself if you want. So I love building open source. I have built a lot of open source libraries over the years. And one of the things that I try to stay away from is binary dependencies. So a lot of Python code can get away with just installing from PyPI, and that will be it. But that's not always true. So while Sentry is almost entirely Python, we do have other things to deal with. So all of our native extensions that we have are either written in C, C++, or Rust. We don't have any Cython or things of that sort. And we do, for the most part, run CPython everywhere. So I think the entirety of the stack uses CPython 2.7 in some version of it. But at least conceptually, I like the idea of making it compatible with PyPI and other systems as well. So this is sort of the context of this. How do we make native extensions work with Python? So why do we have native code to begin with? One of the biggest reasons is speed, but that's not really like the bulk of our native stuff. We have, for instance, if you send a crash to Sentry and there's JavaScript code in it, then we need to make sure that we actually update the line numbers and source locations based on source maps. And source maps are huge JSON documents. And parsing those source maps and processing those source maps took us a couple of seconds in Python, and we are now under like 100 milliseconds with the same thing written in Rust. So speed is one reason why we have native code. Functionality is another one. So for instance, in order for us to handle crash reports on iOS, we need to interface with LLDB, or generally the LLVM ecosystem. And while LLVM has Python bindings, the chunk of the code sits in LLVM and is written in C++. So for some things, unless we want to rewrite the entirety of LLVM in Python, we have to interface with native code. So this is basically, in some places we don't have a choice, we need to do it. So how does native code interact with Python in general? So the import system in Python is able to import shared objects. So if you import mylib from my package import mylib, it will look for a file called mylib.so, mylib.id, or dilib on OS X. So there are a bunch of places where we'll look for it. And then if these modules expose functions with certain names, it can execute it and do stuff with it. However, this requires you to work with libpython. So libpython is a library that comes with CPython that you can link against, and it provides some basic API that modules can use. So how do you build a native library? Well, typically you have a folder where there's native code in it, written in C, C++, Rust, whatever. And when it compiles, it moves the produced libso into your package. And this is for local development usually. So during local development, you usually have all your source code in a package and you want to keep it there. So the easiest way to get native code running is actually that as part of the local development step, it moves the native code directly into the package. But this is not the only option that you have, because for instance, if you make a vdist, a binary distribution for Python, then it doesn't actually move the builds into your source code, it moves the builds into a separate folder. And this is done by setuptools, and the code I don't know if you've ever seen it, but setuptools is really not very beautiful code. And it has very many different paths and combinations in which it builds it. And it doesn't help that setuptools is based on distutils, and pip actually monkey patches setuptools, and setuptools monkey patches distutils. So it's a very complex system. So we try to figure out how we actually can interface with this without breaking the entire thing. So this is for local development. It builds directly into this package folder. For binary distributions, it builds elsewhere. The only binary distribution we care about is the bdist wheel, which makes Python wheels. And this is the only one I'm going to talk about. So we're not talking about X, not about Python Windows installers or RPMs or Debian packages or anything of that sort. So as I mentioned before, we we built our own thing in a way, and we didn't really build our own thing. We tried to go with what exists and see if we can use the best possible option that is there, which means that we don't have a lot of this fancy tooling that some other people are using, like Siphon or something like this. And the reason for this, so the reason why we built it ourselves is we have a lot of systems, we have a lot of developers, and we want to run everywhere. And what I mean by that is, in Sentry, I think there is one of these unwritten rules that it should be easy to have your development stack running locally. And since a lot of our employees are using OS 10, we want that people can pip install a package and it runs on OS 10 or it runs on Linux. So the expectation is you can just pip install it and it's there. We have a package which links against LLVM. Compiling LLVM takes about an hour if you have not a great laptop. And it requires you to have like very specific versions of C++ compiler. You need to have latest CMake. So it's a very complex system that you have to do. So we want to make sure that we can build one binary package, can put it on PyPI, and people can install it from PyPI. So for us, it's important that we can make binary packages that we can publish for other people. And that, unfortunately, rules out most existing solutions. Sad. So distributing is the limiting factor. So we decided on all the possible options we have for distribution, we go with one, which is the one that actually works the best. This is Python wheels. The way Python wheels work, for the most part, is they either have Py files in there. So when they're being installed, they will be compiled specifically for the Python version to PyC files. And a wheel is largely universal, which means that it works for PyPy, it works for CPython, it works for anything that works. But not necessarily. And the reason for this is that wheels can be tagged. And this is what the Sentry wheel looks like. So this is the file name. The first part is the name of the package. The second part is the version number. And this is sort of the minimum set that you have to have. And then you have 3 tags, and those tags can limit where a package can install. The Python tag that we have for Sentry is py27. That makes sure that if someone tries, because we don't run on Python 3, if someone attempts to pip install Sentry on Python 3, it will not find the wheel. And then you at least will say like it doesn't install. The ABI tag is the binary compatibility flag. In this case, it's set to none, which means it doesn't have binary code in it. And platform tag means any, so it can run on any platform, be it OS 10, Linux, Windows, you name it. But so the moment you put binaries into the whole thing, it becomes a lot more complex. Binaries are platform specific, and by platform I mean processor, Linux, Windows, so it spirals out of control very quickly. If you're on Linux, it's also specific to the version of libc you're using. If you're linking against libpython, it also is specific to the Python version, the Python on Python 2.7, and I think even on 3.2 still, I don't know. You have different Unicode builds. So it's very complex. So to reduce it to a small manageable set, we looked at what we want to support. OS 10 is easy. By easy, we mean it can be done so that the wheel ends up on PyPI and people can install it. There are some quirks to it, but generally it works. On Windows, it's actually quite easy because Windows has good binary support. So if you compile something on Windows 2000, it will continue working until the world ends. On Linux, that's not true at all. Linux doesn't care about binary compatibility. Often when you compile something on Linux, the next person that tries to install the binary will see that it doesn't work. There's limited support for binary wheels, and this is sort of the complexity in this, and it's called manylinux. And I will go into this in detail. But we are targeting manylinux on Linux, and we're targeting our easy solution OS 10. So this is one of our packages. It's SymSynth. It's a package that deals with symbolication of crashes. So this is linking against LLVM. If you download the source tarball, it's, I think, 27 megabytes of C++ source code. And it takes an hour and more to compile. So it's really nice when people can install the wheel, which is a megabyte and a half, and it installs instantly. So what you can see here, it has, again, a name and a version. This one here, we improved. It now runs on any Python version, so it runs on Python 2 and Python 3. So this CP27, as of tomorrow, will hopefully be Py2, Py3. So it's a tag that works for Python 2 and Python 3. It doesn't have an ABI tag, which means it doesn't care about which version of Python you're running. So it doesn't matter if it's PyPy, or if it's CPython, or if it's CPython compiled with larger Unicode support. But it has a platform tag. In this case, it means it runs on many Linuxes that are using a 64-bit Intel processor. So this is sort of as good as we can get if this would be like universal instead of CP27. This, on the other hand, is a library that we didn't write. It's a library, it's called Pillow. It's an imaging library for Python. And it's completely tagged, which means that it depends on which version of Python you're running it with. So they need to build a separate version for Python 3.6 and 3.2 and 3.4. They need to build 2 versions for 2.7 because there are 2 ABIs for 2.7. They have many different platform tags because you can't get rid of these. So there's a lot of tags. The ABI tag is the most annoying one, but this was fixed on Python 3. There used to be the case that binary dependencies on 2.7, you can have a UCS2 Python, which means 2 bytes per Unicode character. You can have a UCS4 Python, which can mean 4 bytes per Unicode character. And they are not ABI compatible, which means that if you compile it against UCS2 and you import the library in UCS4, it will crash, and the other way around. The platform tag identifies the platform as mentioned before. The platform is undefined, it's platform specific how it looks like, and it can be very, very complex. So let's talk about this manylinux a little bit, because that's the interesting platform here. What is manylinux? Has anyone ever tried to build binaries on Linux and have them shipped to many, many different computers? It's really bad. It's very terrible. I don't know why, but Linux people hate binary compatibility. So here's how manylinux 1 works, and I wish I would be making this up, but you download a very, very, very old version of CentOS. I think it's like a 9-year-old version of CentOS. CentOS is like a fork of Red Hat. I can tell you what's on this version of CentOS. It doesn't support SSL with server name identification, which means that a lot of things you download from the internet will give you SSL errors. It has an ancient version of SSL, OpenSSL on there. It has, I don't know what GCC version, but I think it's a GPL2 licensed version of GCC, which means it's probably 10 years old. It has ancient version of glib and a bunch of other things. But what it gives you is the satisfaction that you compile against an old version of glib, which has a higher chance of being upwards compatible with current runtime. So theoretically, if you manage to work with this very old version of CentOS and you compile your Python, your native library on there, there is a reasonable chance, if you don't link against specific libraries, that it will continue working for future users. It doesn't work if you use C++ in fancy ways, and it has a bunch of other problems. The biggest problem is that it's a 10-year-old Linux that nobody wants to run. So how do you get a 10-year-old Linux running on a computer? Use Docker. So we use Docker to build on a very old Linux that we made work a little bit more modern by putting newer compilers on it and so forth. But it's still a massive pain. So imagine we would have to build a lot of packages on ancient old Linux. How do we build fewer packages? So we reduce the dimensions. So this is Pillow. We don't build this. But if Pillow makes a new build, like if Pillow releases 4.0.1, they have to build 15 binary packages for Python 3 alone, and then have to build 6 packages for Python 2, which is 21 builds. For us, if we would do the same thing with SimSynth, it would take us probably about a day to push out the release. That's a lot of wheels. It's very sad. How we can get rid of the tags? So we write code that's compatible with 2.x and 3.x, so that's 1 dimension less. We don't link against libpython. The way we achieve this, I will mention a little bit, but it involves CFFI basically. And unfortunately for the CPU architecture, and we can't really make libraries that work on OS 10 and Linux at the same time, so we can't get rid of the platform tag. But for us, it means we build 3 packages instead of 15, which is a tremendous improvement. So basically, we don't link, we use CFFI, we make compatible sources, and then we do lots and lots of black magic with setup tools. So the part about setup tools is that lots of people have their own little hacks about making it work. These are our hacks. They're proven to work good enough for us. And so you might as well use them. So this is how we do it. We take the built-in commands, we subclass them, and we make sure that at the end of it, we run our build step. This obviously is a little bit different depending on if you build for local development or if you build for distribution. So there's some magic in there to see if we have an in-place build, and if we have an in-place build, we figure out where that went, and then we calculate the path. But in any case, we invoke a function called build mylib, and this will sub-process out, invoke the compiler, and do some stuff. The other thing is we need to get rid of these. This whole build system is intended that it always tags it down to the current Python version, current ABI version, all this sort of stuff. And there's no API to make the wheel just not emit those tags. So what we did is we also subclassed the wheel command, and we just replaced the first two arguments with it's always Python 2 and Python 3 compatible and no ABI, which means that now if you build it, it will just also have this tag in it. And the last part is just the platform. Then we need to override the command classes in the setup with our updated ones. And then we can also depend on CFFI, which we are going to use during both installation and during the setup procedure. And we have the basic thing running. Now we need to build the library. So this is how this kind of works. We use a makefile. We invoke the makefile, and we hope the makefile produces the end result, and then we copy from where the makefile puts the stuff into our destination path, which means that we can only build one SO per this build mylib, but that's fine. That's all we do. We link everything into one huge file and then import that. So we have a build command, we have build output path, and we copy it over. The makefile usually just does build X, and then it invokes the build tool. In this case, this is from the Rust library that we are using, where we use Cardo to build it. We have one where we have to do like CMake and LLVM and all those kind of nice things. And then we have a binary. Now we have to import the binary. And since we are no longer linking against libpython, there is no module we can import. If you write import mylib, it will tell you there is no entry point. I don't know how to import this. So we need to use CFFI. And CFFI is, I think it comes from the PyPy project, and it's a more modern version of C types. And one of the nice things about CFFI is that it can parse C headers. So we make headers for all the things that we want to import, and then we let CFFI parse them. And there are two modes in which you can do this. One of them is called header only, where we make, so this is a file called build.py. We put it next to our setup.py, and we import from CFFI the FFI thing, make a new one, and tell it the definitions of our functions. And the problem is CFFI doesn't have a C preprocessor. So what we're actually doing is we're invoking a C compiler to preprocess the output, read it back in, and then we let CFFI parse the results, which means that we can have comments, we can have if-defs and that sort of stuff. So that is actually, that turns out to be super useful and works really well. And then we tell it to set the source to where we want to have the library show up. So in this case, it will build a little shim called nativelib.py, where it will have all its magic and function definitions and so forth in it. And the second argument is means no source code. So that's the header-only version. We also pass a flag to the C compiler that we define a new macro called Python header. So we can, in the header file, we can say if def Python header do special things that only apply for Python. That's super useful for type defs in particular, because CFFI doesn't know about all the types that you might be using, so then you can disable and mock them out. So that works really well if you already have a library that you can import. For instance, we do this for the Rust library that comes out. Sometimes, however, you need to have CFFI compile the library. And the reasons for this is that it needs to pass over some arguments to the compilation that only setuptools knows about. In that case, we can do set source with like a bunch of other things. And in this case, as part of the CFFI build process, it will invoke a C++ or C compiler to actually compile, not to compile into a dynamic linked library. So that's also one of the things that you can do. Then you have to git ignore all the things that it produces so you don't accidentally check them into source control. And then you're basically done. And you can start importing things. Because it's a C library that you're interfacing with, a C++ or Rust library, they are not very fun to use. So you need to write a higher level wrapper around it. This is kind of how we do this. So we import from our native lib the FFI thing. In case where you only have a header, we need to say where the SO file is. And then we can invoke functions in it. Like there's a mylib global in it if needed. That's a function that's exported by the library that sets up memory allocators or whatever is necessary. And we call it once when the module imports. And then for each object that we're dealing with, we have an interior pointer on object creation, and on object deletion, we call a function in the library to free it up again. So one of the things you will immediately notice is that this totally doesn't scale to high number of objects. And this works for us because what we are doing is we are treating the native libraries as like a server that we talk to. So we give it a command, it does something, and it eventually comes back with a result. So our source map processing does it. All the huge JSON source map that we are parsing, we never expose to Python. It's sitting somewhere in memory, and we just ask it questions like, where is this thing? Search for it, and it gives me an answer. But I can't iterate over all the things in it, because to get these objects out of like Rust or C++ back into Python would be, it would negate all the performance improvements, because you would have to wrap it in Python objects. So we don't do that. We don't build libraries where you have huge objects that you need to expose. So we keep all those objects there. Just for the individual APIs that we care about, we make a little shim. And this is how our shims look like. A Python object wrapping some other object in C or C++ or Rust. And if you compile directly a library with CFFI, then you don't need to do the DL open. So here you had to do DL open to wherever the hell the SO is. If it's compiled together, you can just directly import this, and it just works. Now for building, very sad process. So the basics is you need to have this pip install wheel package. It doesn't come with setuptools, so you have to import it separately. Once it's there, it magically provides this bdist wheel command, and out comes wheels. And these wheels come out specifically to the computer you're running it on. You can't cross-build wheels, so you have to basically have Macs, have Windows machines, have Linux machines if you want to build it. So for Linux, at least, we have Docker, and this is really necessary because you have to use this, again, as mentioned, ancient CentOS version. So there were some people who realized that ancient CentOS is not fun, and they made specific Docker images which are still ancient CentOS images, but they at least have modern compilers on it. These two are the ones that we're currently using. They are from the team that also builds Pipey and that sort of thing. And they come with a little bit more modern compilers, but they still have ancient old versions of OpenSSL and all those things. So it's still not fun, but because all the pain and suffering is contained in a Docker image, it gets a little bit better. So from the outset of the Docker image, you have still your modern computer. Then we use Docker files to build multiple layers of this process, because, as mentioned before, LLVM takes really long time to build. So by caching these build artifacts in between, it's a little bit more fun to debug all the nice little problems you run into. Because we have only a 64-bit machine we're building on, the 32-bit Docker images are actually on a 64-bit machine, so you need to use the Linux 32 command to fake the entire thing into running on as if it was running on 32-bit. So that's quite useful. I didn't know that initially that this is how it works. So you need to prefix every command that you run in your Docker file with Linux 32 so that the environment variables that compilers pick up and stuff actually point to the 32-bit libraries. So how do we do this then? We actually use Travis to build on OS X and on Linux. So we make sure the Docker files work independently, and then we trigger them off by with the Travis YAML. Now then the other problem is that theoretically you can directly upload from Travis to PyPI, but the issue is that our builds take a very long time, and then one of the many might fail. So for instance, if you have a build matrix that builds 3 different libraries and one of them only fails, what you don't want to have is a new release on PyPI with 2 binaries on it and the third one is missing. So what we actually do is we build onto GitHub releases, and then I manually go in afterwards, download the artifacts from GitHub releases, and then upload them from my laptop with Twine to PyPI. It's not perfect, but it's the best thing we can do with Travis at the moment. What about macOS? We also built this on Travis. This is where it gets a little bit weird. Apple doesn't really care about supporting old things. So you can find semi-legal old OS X SDKs on GitHub. If you use an old OS X SDK, you can be a little bit more compatible downwards. So we built for OS X 10.10 on more modern machines. And since those SDKs are long gone, you have to find them and put them in magic places. And then you can use macOS deployment target to say, like, I want to build for 10.10. And then because pip thinks that this is compatible with some other version, you have to manually override the platform name to be macOS 10.10 Intel, because otherwise it will pretend that it also works with 10.6, which I think at this point is like 15 years old. Or maybe not, but I don't know, it's very old, and if you run it on a Mac older than 10.10, it will definitely fail. So this is the basics of it, and then to make the suffering a little bit better, we found some patterns that I think are actually more interesting than the rest of it, of how we actually managed to stay somewhat sane in this process. The first one is we changed the way we deal with libraries to be a lot simpler than what other systems are doing. So a lot of these native extensions, like the Postgres extensions or NumPy and all of them, they are full of objects and they expose everything to the Python layer. As I mentioned before, we don't do that. We have one header file which exposes the bare minimum of what we need, and these objects are then usually wrapped in a higher level language. So this is the C API we expose, but then the library is, for instance, written in C++, and it just does shitty casts. And then you can write C++ there, which is a little bit less suffering in some sort of, especially if you work with LLVM. We do a similar thing with Rust. Error handling, that's annoying. You can't propagate panics or exceptions across C boundaries. And if you would do, then the Python interpreter would crash. So we actually have this error type. Is a struct sitting around somewhere. And then when a function needs to fail, it's an output parameter where we put a new error in, write some stuff, and then the caller can see that an error was put in place, and then raise a Python exception for that error. This is then how this kind of looks like. We tell CFFI, make a new error, call the function. If there was an error, if there was no error, return the return value. Otherwise, convert this error struct into a Python, into either a runtime error or like a specific error if we can determine the error from the error code, and then just raise it. So instead of using then, you could imagine there could be lib, mylib, do stuff, arg1, arg2, we invoke it through this invoke with exception, and then we get exceptions this way. This is a small little thing we found that makes it nicer, because then you have consistent error handling across all functions. Originally, we had specific return values for each and every function, and it required checking, and then people didn't check it, and yeah, madness. So how painful is it? It's really bad, to be honest. I thought it will get better. It's getting consistently worse because you discover more and more issues with the whole process, and it's really painful. What makes it a little bit better is Docker. Before we used Docker, it was way harder. The good thing is, when it works, it keeps working. I love it, that part, because we used to build on Travis, and then Travis doesn't update, and then all of a sudden you produce a binary which no longer works for some people for which it worked previously. The fact that we now can have like ancient CentOS images, they will definitely not change anymore. So they will continue to be 9 years old. I mean, next year they will be 10 years old, but these images, they are set in stone. So I can just theoretically, even if Travis stops working, I can put a computer in the cellar and keep this stuff running on there, and it will continue working. So that's good. So what do we use this for at the moment? C and C++ native symbolication is the biggest one. So that's basically our process in converting. Here's a crash. Here's where the instruction happened. I want to see where it actually happened in the original source. And this is a very involved process which looks a little bit like a debugger. And that's why we have to pull in the whole LLVM stack. We use it for some Rust modules. At the moment, it's only the JavaScript source maps, but I do plan on making a few more because it's actually a very enjoyable process to have some of this lifting done in Rust instead of, like previously we had these modules that were written in Python because they were written in Python and it was good enough. But then if you handle more and more events, eventually you will start to think a little bit about, does it have to be in Python? Can we just move this little high critical part? Can we move it into a faster language? And I would say before Rust, that was not something we would have considered, just because writing C and C++ is not enjoyable. I think writing Rust is enjoyable enough that it can be something that you can consider from the start. Maybe we'll also look into Go at one point. There is some advancements about trying to make Go work a little bit with Python. And then obviously we have native modules that are not ours, that are like Postgres extensions and so forth. And there we currently, I think, just install them on whenever the package lands. But I would love if we make our installation process better, where we can have every single binary dependency that exists on our system is actually already pre-built wheel. Yeah, that's pretty much it as far as our lessons learned in short overview go. If you're curious about writing binary dependencies for Python, I recommend you looking at, I will put it on my website. It's lukumer.puku.org, or just try to find my GitHub profile and I will link it there somewhere. I will make a link selection with basically some examples of how this is done. Because I looked for a couple of months to find better patterns for working with native libraries. And it turns out that nobody has really a good idea of how to approach it best. This is the best that we came up with. And there's not a lot of other examples that are structured like that. So that's why I would like to eventually make some sort of overview page or documentation out of how to build binary extensions. Yeah, so if you have any questions, ask me. And I have some extra bonus slides in case someone is interested how we make this work with Rust. And I can show you this afterwards. So just let me know.
So, thank you, Armin.